and welcome to this lecture number 10 in the course Robot Motion Planning. In the last class, we looked at the topology of configuration space, that when you go from one space, we've seen that we go from the Cartesian space, which is the real world in which the robot is, to the configuration space, find the path in the configuration space, and then come back to the Cartesian space again. So this mapping from one space to another space is very important in robot motion planning, and that's why we need to understand the topology of different spaces. Okay, so today we'll very quickly complete what we were doing in the last class, and then we will continue with the next part, which is the various methods of path planning to take the robot from an initial point to a final point. Okay, so in the last class we were looking at configuration space. We are looking at topology of configuration space, and very quickly we'll revise what we were doing in the last class, and then we'll move on to various methods of path planning. And today we'll look at roadmap methods. But before that, let us very quickly complete what we were doing in the last class. So very quick revision. We said that a manifold is a topological space that locally resembles Euclidean space near each point. Now we have seen that for example, we have the robot which is in the Cartesian space. Let's take the example of a mobile robot which is in the space, and this is my mobile robot, and there is an obstacle here. Okay, and what we do is, this is my Cartesian space, this is my x-axis, and that's my y-axis. So this is a mobile robot, and this is my y-axis, and this is an obstacle. So what we do from the Cartesian space, so this is Cartesian space, we move to the C space, in which the workspace becomes smaller and the obstacle becomes larger. Let's say the obstacle has become larger like this. Okay, and the robot becomes a point. Then there, what we do is, this is my C space. We find a path from the initial point to the goal point, maybe like this. And then what we need to do is, we need to come back to the real world again, in which the robot moves. So we have a forward transform which is given by phi, and we have an inverse which is phi inverse. Okay, and this is the forward mapping and the inverse mapping between two spaces. Now you can very well understand why this is very important, because if you find the path in C space and you cannot come back to the configuration into the Cartesian space, then it's of no use, right? So we need to very carefully understand this topology of different spaces. Now a manifold is a topological space that locally resembles Euclidean space near each point. Okay, Euclidean space or Cartesian space. Okay, they mean the same thing here. Okay, so we say a manifold is a topological space that locally resembles Cartesian space. Okay, now the structure of configuration space is a manifold. That means that it resembles Euclidean space near each point. That means you can go from the configuration space to the Euclidean space. Okay, now by definition, a set K is a k-dimensional manifold if it is locally homeomorphic to R, meaning that each point in S possesses a neighborhood that is homeomorphic to an open set in R. Okay, that means every point from can be locally mapped onto the Euclidean space. Now this is an example, a circle. Okay, now a circle is a manifold. Okay, and that is topologically the same as a line of dimension 1. Okay, so in terms of topology, a circle and a straight line is the same in a way, in terms of topology, and every point on the circle can be expressed as that on a line. Say for example, you look at this black curve, this circle here, every point here can be projected onto a straight line. That means if this is locally. Okay, hence manifold is, every point is locally can be mapped onto the Cartesian space. Okay, so this is very important term here, that a manifold is a topological space that locally resembles Euclidean space. So this term is very, very important here. Okay, so if you locally look at this small region of a circle, then each point here can be mapped onto a straight line. Similarly, if you look at a sphere, the earth is a sphere, right? It's spherical. Now how do you make maps? You locally map a local region to a flat map, which is a flat surface. So this is locally possible. Okay, and that is where the term charts and atlas comes from. Okay, so it is basically saying that a configuration space is a manifold, and it is a manifold because it is locally like Cartesian space, and that is why we can go from one space to another space. Okay, now connectedness, a manifold is path connected or connected if there exists a path between any 2 points in the manifold. Okay, so like what we talked about in the last class, we said that this is my C space and this is my Cartesian space. So this is my Cartesian space and this is my C space. Now in this case, we have 3 obstacles, the pink one, yellow one and the blue one. So we have a 2-link manipulator here. This is 2 degree of freedom, and we can draw the Cartesian space like this. So this we can draw the C space like this. And in the C space we have obstacles here. So this is my obstacle, obstacle, and obstacle. Now this is telling us a manifold is path connected or connected if there exists a path between any 2 points in the manifold. So this point and this point, there exists a path between these 2 points in the manifold, and hence it is path connected. Okay. Now if I say this point and this point, now there is no path from here and here. It can't go through an obstacle. So these two are not path connected. That is the meaning of path connected. Okay. Now why is this important? It is important because if there is no path between the 2 points, then the robot cannot go in the real world between those 2 points. Okay. So a manifold is path connected or connected if there exists a path between any 2 points in the manifold. The presence of obstacles can disconnect a manifold as shown here. Okay. Now very clearly, please remember that how did we get the manifold? We got a torus. We cut the torus like this, opened it, made it into a cylinder. Okay. And then what we did, we cut it further and opened it like this. So I first cut it like this, opened like this, then I cut along the center of the cylinder, opened it, and we made it like this. Okay. And that is what is shown here. So it basically means that this side is connected to this side. So you can have a path here and here. It can go like this and can come from here also. Okay. It is also path connected. Okay. And from this side and this side are path connected. Okay. But this and this are not path connected. Okay. So please do remember that this side and this side are connected actually as far as the manifold is considered. And in terms of the manifold, in terms of the torus, this side and this side is also connected. Okay. So this part and this part is path connected. Okay. Now embeddings of manifold in the R raised to n or in Euclidean space. Now a k-dimensional manifold can be represented using as few as k parameters, but doing so may require multiple charts. Okay. So the dimension of a manifold could be k, but you may not be able to represent. So you may be able to represent using as few as k parameters, but doing so may require multiple charts. What does this mean? Let's take an example. For example, S1 is a one-dimensional manifold. Now, as far as topology is considered, a circle is a one-dimensional manifold. Okay, it is only 1D. Okay. Now, but to represent a circle, you actually need two parameters, x squared and y, x and y. So I'm drawing it. There is x-axis, there is y-axis. So to represent this, I use two parameters actually. Okay, you can see that this is the equation of a circle. So you can, although a circle is a one-dimensional as far as topology is considered, okay, one-dimensional manifold, but to represent it, you need two parameters, that is x and y. Okay, we cannot find a single chart for all s raised to 1. Similarly, we cannot embed the torus. Another example was the torus. Very good example is this torus. Okay, so we cannot embed the torus in R2. Now we know the torus is basically made up of theta 1 and theta 2. That's how we got the torus, by varying theta 1 and theta 2 for a 2 degree of freedom system. And when we draw the torus, it is something like this. This is my torus. So this side is theta 1 and this one is theta 2, right? But when I'm drawing it, if you note that you cannot draw it in 2D, it has to be drawn in 3D. A torus can be drawn only in 3D. This is my x, that's my y, and that's my z. Okay. So similarly, we cannot embed a torus in 2D, that is r raised to 2. We need to embed in 3D now. Okay. So we can use multiple charts or use a single global representation by embedding the configuration space in a higher dimensional space. Okay. The first example was that of a circle, which is 1D, but you require two parameters to represent it. Then a torus, which is 2D, but you require three parameters to represent it. And what about the rotation of a rigid body? Now, to represent the rotation of a rigid body, you need a 3x3 matrix. Okay. So what we have seen is that if you have a rigid body like this, we have an axis x, y, and z, and we have a rigid body. How do you represent the rigid body? The angles of the rigid body, you fix another axis there, x, y, and this is my z. Sorry, let me follow the same convention. This is x, y, x dash, y dash, and z dash. And then what we do is we find the angles the x-axis is making with the x, y, z of A. This is A and that's B. And then we write it as R11, R12, R13, R21, R22, and R23. And here it is R31, R32, and R33. Now what is this? This is the x of B on the x of A, x, y of A, and the z of A. That is the meaning of this column, right? And this is the y of B on projected onto the xyz of A frame, and this is the z of B projected onto the xyz of A frame. So what we are seeing here is that you can represent the position of a point by 3 coordinates x, y, z, but to represent the rotation, okay, of a body, rigid body in space, you need how many parameters? You need a matrix. So this is a matrix that we have seen. Okay, so this we have seen earlier in the first class, I guess, first or second class, when we talked about transformations. Now this is showing that to represent a manifold, you may require a higher dimensional space. This is the meaning of the last statement here. Okay, that you might need a higher dimensional space to represent a manifold. Okay, now when we're representing the rotation or multiple rotations, we can represent as roll pitch yaw. We can call this as rotation about the alpha, about the x-axis, y-axis, and z-axis. Okay, by an angle alpha, let's say, by an angle beta, and by an angle gamma. So I have two axes now, and they are being rotated about a fixed angle. Okay, so let's say this is my fixed axis. This is my fixed axis, x, y, and z, and we have another axis, which is the red color, which is going to be rotated. So this is my axis B. Okay, so first what I do is I rotate about the x-axis by an angle alpha. So what will happen is B will come here now. Okay, so sorry, y dashed and z dashed has come here. Okay, this is an angle alpha. Then what I do is I rotate about, let me change the color, I rotate by an angle beta about the y-axis. Now which y-axis? This is called fixed angle rotation. We are rotating, so rotate about fixed axis. Okay, rotate about fixed axis. So I'm going to rotate about the y-axis, which is here. So what will happen? My x double dash will come here, y double dash will go there, and z double dash has gone there. Then number 3 is what? Number 3 is the rotation about number 3 is rotation of gamma about z axis. Z, which z? This z. So what happens? It goes here, here, and here. That's my x triple dash. Okay, y triple dash and z triple dash. Okay. Now when I make the combined rotation matrix, I'm going to multiply r gamma into z. Okay, so I reverse the order, and then this is r beta into y into r alpha into x. So I've reversed the order. So we reverse order of multiplication. Please note this. Okay, so this is called the fixed angle rotation, also called the roll pitch yaw rotation. Now you can also rotate about the rotated system, rotation about rotated axis. Okay, these are sometimes called Euler angles. Okay, now in this particular case, we are rotating about a rotated system. That means the first axis is always going to remain the same. So r x alpha, then we are going to rotate by r y beta and r z gamma. Okay, so this is my first, second, third, but rotate about a rotated axis. Okay, so this is my x, y, and z. Now if I take my first rotation, I rotate about the x-axis like this. So this fellow goes there. So that's my b, y dashed. So the first one is the same. Okay, why? Because you're rotating about the fixed axis only, because there is no other option. Initially they were the same. The second one, now what happens is I'm rotating about y-axis now. Okay, so what will happen is z will go there and x will come here. Okay, and the third one, I'm rotating about the rotated z-axis. So the rotated z-axis is this one. So I'm rotating like this now. Okay, so what will happen is this will come here and that will go there. Okay, x triple dash and y triple dash. But in this case, the order of multiplication remains the same. Okay, so please remember that here order does not change. So this is something to be you should note. And why this happens, because you have to be very careful about the order, because these are matrices. So rotations do not commute in space. Okay, and that is something you have to be very, very careful about. Now, these are some examples of robots and the degrees of freedom. Okay, so let's look at a mobile robot translating in a plane. So you have a plane which is x and y. This is my x and that's my y, and we have a mobile robot. Okay, so there are two wheels here. It's a caster wheel. This is a point P. Now it can only translate. It is only translating in a plane. So this point is translating. It cannot rotate. Okay. In that case, degree of freedom is 2. So only x and y. Right. Now mobile robot translating and rotating in a plane. So it is 3. So x, y, and theta. So there is an R2, which is x and y in Cartesian space, and s is one rotation, which is s. Now rigid body translating a rigid body translating in 3D space. So you have a rigid body which is translating in rigid space, in free space, and this is also called a freely floating body. So in this case, how many degrees of freedom? It has 3 rotations, 3x, y, z. Okay, 3x, that's x, y, z, and alpha, beta, gamma. So it is 6. Okay, so rigid body only translating is 3. Okay, a spacecraft has 6, so 3 rotations and 3 translations, 3 rotations. Okay, so if a rigid body is only translating, then it has only 3 degrees of freedom, right? My x, y, and z. Here it has x, y, z plus alpha, beta, gamma, right? Now n jointed revolute arm, it has t raised to n. A planar mobile robot with an attached n jointed arm has a mobile robot, a planar mobile robot. It's planar, so it has SE2. Okay, and it has plus the arm has t raised to n. Okay, so this is basically giving you an example of the degrees of freedom or different kinds of robotic systems. Now let's move on further from here and look at the path planning methods and algorithms. As I said, the whole objective of this course on motion planning or path planning is to write a program or an algorithm which is going to find a path that will take the robot from the initial point to the goal point. And to do that, what we basically need is that we have to go to C space, the robot becomes a point, and then we find the path, and then it comes back. So there are various methods of finding paths, okay, depending on situations, and we will look at each one of them one by one. So the first one is what we call roadmap methods. Okay, roadmap method, as the name suggested, as the name suggests, is something like finding a road in a map. Okay, like today we have Google Maps. Okay, how do you find a road to go from one point to another point? Then cell decomposition, where you're decomposing the cell or the work cell into different cells and then finding the paths. Sampling based planners, where you don't have a map but you start sampling and see where you can go and where you cannot go and try and make a connected graph. Potential field based planners, okay, where you use potential field to guide the robot. Okay, so this is basically to guide the robot to the goal using potentials. That means, for example, the object has a repulsive potential, so when the robot goes near the object, it gets repelled, and the goal has an attractive potential, so when the robot is always pulled towards the goal. Wavefront planners, these are something like waves, the waves on water, they tend to move towards the lower potential, right? Planning with kinematic constraints, this is like cars. So we talked about kinematic constraints, for example, holonomic and non-holonomic constraints. Non-holonomic constraints, like real cars, they cannot go sideways, right? So planning with kinematic constraints involve holonomic constraints and non-holonomic constraints, and then we look last of all into some applications. Okay, so we'll start off today with the roadmaps, and the next couple of lectures are on basic methods, as I just talked about. So today we'll start off with roadmaps. Now the basic idea of roadmap method is to capture the connectivity of free space by a graph or network of paths or roads. Okay, this is very simple to understand because this is we are very familiar with Google Maps these days. Okay, or if you look at any map, how do you go from one place to another place? You look at a map. Now, for example, on the left hand side here, you see the Google map. of New Delhi. Now you want to go from Connaught Place to New Delhi railway station. So Connaught Place is here and New Delhi railway station is there. Now how does Google Map find out which way you should go? Okay. So what it basically does, or what is a map, or what is a road map? A road map is a set of connected graphs or connected roads. So basically you can see that these are all the various roads in that area. Okay. And there is a network of roads. And by following this network of road, you can go from this the initial point to the final point. Okay. Now there could be more than one road. For example, you could go from here, go like this, like this, like this, then cross over from that side, go like this, and then go there. Okay. So this could be one way. Now there could be other ways. For example, you go like this, like this, like this. These are all small paths. So you can find some path which will take you there. So then the next question that comes is, which path will you take? Okay. Now in the Google map, one of the parameters could be the distance. Okay. But as you can see that it has different colors. It has orange color, it has blue color, and it has red color. Red color means it's very congested road. So it will take more time. So you have to worry about time. Okay. So it is not only a question of finding a path, it is a question of how you are going to go on the path, which one is going to take, which has a longer distance of travel, which is going to take more time to travel. A particular distance could be less, but the time could be more. Okay. So this is basically a very brief idea of how road maps work. Now on the right hand side, we have a problem of a mobile robot. Okay. So we have a mobile robot, which is an initial point. Let's call it a mobile robot. Okay, so mobile robot, and these are obstacles which are called CB1, CB2, CB3. Now the mobile robot is a point. Okay, and I want to go from one point, the initial point, to the goal point here. So initial point is here, goal point is there. Okay, now you can see that this free space, the first thing that you should note here is that this is free space where it can go. A couple of other things. This is flat ground, so it is 2D. So 90% of the algorithms we'll talk about are for 2D applications, not for 3D. Okay, and most of 3D also can be reduced to 2D. So there is free space and obstacle space. Okay, this is what we are seeing here. So the free space is connected by a network of paths. So this is a network of paths. Okay, this is already connected by a network of paths. Okay, how did we get these paths? That will come to later. So we are given this network of paths. Now what do I do is, I know this is a network of paths. So what I will do is, from the initial point, I will connect to this network of paths here. And from the goal point also, I will connect to the network of paths. Then how many ways are there to go from the initial point to the final point? There could be more than one. For example, I can go like this, like this, like this, like this. Or I could take some other path and go like this, like this, like this, like this, like this. Okay, I could take even more paths. Other paths are there. So then the next question comes, that which path will you take? So the first thing that we need to know is whether a path exists. So in this particular case, we can see that a path exists. Number two, then which path? Now for us having eyes, it is very easy to see and say, okay, this is a path that is connected, and it can go from like this, it will be shorter. But this poor robot, or the poor algorithm, does not have eyes. So an algorithm is a program. A program has to, a program will be run, and the program output has to be that this is the path, and that is how you should go. What is the input to the program? Now you can guess from here that the input to the program is the geometry of space. Okay, that means where is the robot, where is the obstacle, where is the workspace. Okay, so essentially path planning is a geometrical problem. We solve it geometrically. We have eyes, so we can see very easily and say. Whereas for a robot which doesn't have eyes, it has to geometrically figure out, or the algorithm has to systematically figure out how many paths are there, which path it will take, and should not hit obstacles. Okay, that is the whole objective of writing an algorithm or a program for path planning. Let's proceed. Now the definition of a roadmap is that a roadmap is a union of curves such that for all start and goal points in free space that can be connected by a path, it has accessibility. That means there is a path from Q start which belongs to Q free to some Q dashed, okay, which also belongs to Q, which belongs to the roadmap. So accessibility, there is a path from the start point which will join which will join the roadmap. Departability, there is a path from the Q double dashed to the roadmap to goal. Okay, so from Q dash it has joined at Q double dashed. Now from Q double dash, which belongs to the roadmap, to the goal, there is a free path. And connectivity, there exists a path in roadmap between Q and Q double dashed. Okay. Now please note this is one dimensional. Okay, this is a path is one dimensional in terms of topology, but to represent it you need 2D. Okay, but the path itself is 1D only. Now this is very easy to understand: accessibility, departability, and connectivity. So accessibility essentially means that from here you should be able, at this point, you should be able to access the network. Okay. Departability, you should be able to go from here and go to the goal point. And connectivity is this connection should be there between the accessibility and the departability. Okay. So that is the basic idea of a roadmap. Now visibility graph methods. So how do you make this roadmap? That's what we are looking at now. Okay, so we try to get the roadmap. We know, okay, once we have the roadmap, okay, so we have the roadmap like this. Now once you have the roadmap, then you can go from the initial point, join the network, okay, then go towards the goal point, and from that you can depart again and then go to the goal. Okay. But then you need the network of paths. How do you get that? So there are some methods of getting the network of paths. So the first method we'll look at is called visibility graph method. So the basic idea is very simple. Okay, you see what is visible as you stand at start point, and then as you proceed towards the obstacle. Okay, so this means that basically you stand, suppose I'm at this point, this is my initial point or start point, okay, and there is an obstacle. Let me draw it with some other color. So there is an obstacle here, okay, and there is another obstacle here. Okay, it says that you're standing, imagine yourself standing here. Okay, so this, you're standing there, and this is your eyes, and from there you can see. Okay, now what is visible to you is, this is visible to you, that is visible to you, this is visible to you. Okay, so these edges are all visible to you as you're standing there. So what is visible as you stand at the start point, and then as you proceed towards the obstacle. So you can see, what can you see? You can see this obstacle here. You can see this edge, you can see this edge. Now when you proceed towards the obstacle, you come here, and from here what can you see? You can see this, you may be able to see that. Okay, so you can see this, you can see that. Okay. Now the edges here are also visible there, because from standing here you can see that also. So from here you can, then you move here, and from here you can see that, you can see that. So it is like saying you're standing at the start point, looking at the obstacle, then going to the vertices of this obstacle and seeing what more can you see. Okay. And whenever you see a vertices, whenever you see a vertex, basically you are connecting that with a straight line, which is your road. Okay. So this basically means that the robot is a point in C space. Okay. And you basically stand and see, which is very easy to understand. Whenever you see a vertex, you know there's an obstacle, and the obstacle has a vertex. So you go to that vertex and then you see again. What more can you see? Okay. And then you connect all of these vertices by straight lines, and that is where you get your collection of paths. Okay. Now, in the visibility graph methods, this is defined for polygonal obstacles. These are various obstacles which you can see, Q1, Q2, Q3. The nodes correspond to vertices of obstacles. So each of these nodes are the vertex of the obstacles, the vertices. Nodes are connected if they are already connected by an edge or an obstacle. Okay, so you can get connected nodes. The nodes are connected if they are already connected by an edge of an obstacle. So you have a node here, and this is already connected by the edge. The line segment joining them is in free space. Not only is there a path on this roadmap, but it is the shortest path. Okay. Now, if you include the start and goal nodes, they are automatically connected. Algorithms for constructing them can be efficiently written. So you can have a computer program. What is the input to your program? Okay. Input to program. So the input to the program is the workspace plus vertices. Once you give this to the program, the computer program knows that these are the vertices and this is the workspace. So what it can do is it can connect all the nodes by straight lines, okay, and then from the initial point we can connect to the goal point by following one of the roadmaps. That's how we have got our roadmap, right? Let's see how this is done. First of all, draw lines of sight from start and goal to all visible vertices and corners of the world. So you're at start point here. So we are drawing straight lines to all the visible vertices. So what can you see? You can see this one, 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 this one, this one. That is visible, right? Okay. So first of all, draw lines of sight from the start and goal to all visible vertices and corners of the world. Okay, that we have done. This is the corner of the world. This line should have been here. Let me just correct it. So the corners of the world is here like this. Okay, and that part is not there. So this is not there. Okay, so we are drawing lines from the start point to all the vertices that are visible. Then what we do is draw lines of sight from every vertex of every obstacle like before. Remember, lines along edges are also lines of sight. Okay, so first of all, you see which vertices are you can see, then you go to that vertex, and what more can you see? You can see all this, say from here, you can see this, you can see that, you can see that, you can see this, you can see this. Okay, so these vertices you can see, and you are also supposed to draw lines along the edges, so you can see this also. Okay, now continue doing that. Now draw lines of sight from every vertex of every obstacle. Remember, lines of edges are also lines of sight. So if you do this, what will happen is, what you'll see is a total connected ray of lines. Okay, and finally what we get is this. Okay, please ignore this line. Okay, this line is not there. Okay, so the visibility graph is complete now. So this is showing you a complete network of paths. Okay, so this is giving you a complete network of paths. Now once you have got the network of paths, now what you can do is you have to choose, you want to go to the goal point. So how can you go to the goal point? There would be so many. You can go this, that. Okay, or you could go this way, you could go that way, you could go that way, you could go in so many ways here. Okay, then the next question would come in terms of distance. Okay, so which is the shortest path maybe. Okay, so this is basically called the visibility graph method, where we have drawn the visibility graph simply by connecting all the vertices by straight lines. It's like you go and stand on the vertex, and which other vertex is visible to you, just connect it with a straight line. Okay, now this is a visibility graph where we have drawn the complete graph. Now we have to find a path. Now what you can do, you can look at the path length. So this path length here to here to here to there would probably be the shortest. How do you know? Probably this is the, if you draw a straight line like that, the one closest to the straight line will probably give you the shortest distance. Okay, so this is probably the shortest distance path. Okay, this is the straight line that was connecting. Now okay, so this is geometrically how it is done. Now let's look at in terms of an algorithm. Okay, when we are drawing this connection of graphs, interconnected roadmap, the algorithm that works is basically, which is called the sweep line algorithm. Now this assumes that a ray of light is shining from start point and it is rotated through space covering the full range of 360 degrees. Okay, so imagine you're standing here, start, okay, and there is a ray of light that is shining from start and it is rotated through space covering the full range of 360 degrees. So let's say this is my 0 and this is a ray of light. It's like saying you can consider this to be a torch. Okay, suppose you're shining a torch. Okay, so, and this ray of light is rotated to full 360 degrees. Okay, now what is it that you'll see? As you start off from 0 degrees, you will first hit this obstacle. Then as it is moving up, what will happen is you'll see, sorry, my start, okay, this is the logical, the way it works. But in this particular case, you are standing here. Okay, the example that is shown here. So we are standing here, this is my start point, and shining a ray of light. So what you're seeing is that it is hitting the obstacle like this, like this, like this, like this. You can see that vertex. Okay, how many vertices you're shining this ray of light, and how many vertices can you see? So you're seeing the edge. One is an edge, that is E4, is an edge E4, and there is a vertex which is that side V3. Okay, so this one and this one. Then as it is sweeping more that side, it is hitting this edge which is E8, and it is getting the vertex V7. Okay, now we sweep it a little bit more. In this point, what is happening is hitting no edge, but is hitting the vertex V4. Then we are hitting V4. Further we sweep more, we are hitting that's V8. Okay, so in this way the ray of light is being rotated by 360 degrees, and we are making this if it's an edge and a vertex, or only a vertex, that we are noting as it is making a full sweep. Now in this, what we can do is, wherever there is a vertex plus an edge, okay, we can remove, because it is going through the edge, it can't go through the edge, right? This is geometry, so geometrically, basically the ray of light, this is a ray of light, so this is the equation of a straight line, right? So you're basically drawing a straight line and then seeing whether this straight line is intersecting this edge or it is hitting that point. Okay, so geometrically we are doing this, and we make this pairs, and wherever we have a vertex plus an edge, we remove, so we are left with only the vertices. Okay, so the vertices which can be seen. Okay, so the vertices which only can be seen, those are the ones that we are keeping. Okay, so let me draw it again and just explain. This is a very simple method, a very nice geometrical method. So here we have one obstacle, here I have another obstacle, the same example, and we started off by using a ray of light like this at theta equal to 0 degrees. Then we start sweeping it like this, 360 degrees. So wherever it hits an edge and a vertex, we record and keep. So this is a straight line, and these are all straight lines and edges. So geometrically we can find out the intersections, right? So as it is going up, what we are seeing is that it is going like this, and then it hits that one. Now it hits that, but it is also hitting this edge. So let's call this E1 and let's call this V1. So E1, V1 is there. Okay, then it goes a little bit higher, it hits V2. So there is V2, but there is no edge. Okay, then it goes a little bit higher, it hits that one. It probably hits the inside fellow first, this one, but it also hits this edge. Okay, then what we do, we make this full sweep and make this wherever it is hitting the edge and the vertex. Then we remove. So if I remove this, what will be left? Only these vertices will be left. Okay, the vertices through which there is no edge and vertex. There's going to be one here, one here, one here, and one there. Okay, so my sweep line algorithm is basically giving me the connection between the start point and the edges. Then what do I do? This is step number 1. Step number 2 is I come to the edge, one edge at a time. I come to this edge. This is the first one, right? Then I do the same thing, sweep line algorithm. Now I start sweeping from here to 360 degrees. What does it see? It sees that edge. Okay, then where do I go? I go here, it sees this edge. Okay, it also sees the edges, right? So it goes here, it sees that edge, and then basically what it can do is, suppose my goal is somewhere here, it connects it with that. Okay, so this is basically giving us the sweep line algorithm, which basically tells us what are the various interconnections between the nodes. Okay, and that is giving my roadmap. So in the previous examples, we said that how to get the roadmap. This is how we can get the roadmap. Basically, we can shine a ray of light and see where it is hitting and identify these vertices. Okay, then your this is actually like a ray of light. So it's hitting that, it's hitting that, it's hitting this. So that is like a road in the roadmap. Okay, and we are making the connections to all of them. Now, something which we have seen here is that this network includes a lot of roads, okay, or networks. Now, all of them are not useful. Okay, it is getting very clumsy and congested. For example, you may not need, in this particular case, suppose I want to go from this start point to this goal point. Okay, I could have gone like this, like that, like this, and then gone like that. Or I could have gone from here to here, then here to there, and there to there, then there to here, and there to here, and then there. That's also a path. It's possible. Okay, but something that we notice here is that if you use the sweep line algorithm or this method, the current graph has too many lines. That means there is just too many lines. Now, something that you note in very easily is that whenever you have concave, there is no point in going there. Okay, so the lines that go into concave vertices actually are not of much use because they only lengthen the path. They don't make it shorter. Okay, so the next step is to reduce the visibility graph, and this is called the reduced visibility graph. Okay, so a reduced visibility graph consists of nodes that are convex, edges that are tangent, and do not head into objects at either endpoint. So first of all, we are reducing it such that anything that is roads which are going into the concave parts will remove it. Okay, because they are taking more distance, they're increasing the length without doing anything useful. So how do we do that? We use the supporting and separating lines. So we have, this is called supporting line between any two obstacles. Let's call this obstacle 1, obstacle 2. That is a supporting line. Okay, and these are separating lines which are separating these two obstacles. Now, if you can imagine, if you want to go from here to here, then this is the shortest path. Similarly, if I want to go from here to there, this is the shortest path. Okay, whereas if I want to go on the outside, if I want to go from here to here, then this is the shortest path. Okay, or from here to here, this is the shortest path. That is the logic of the separating and the supporting edges. So basically, if you just have supporting edges and separating edges, you don't need any other lines, because any other line coming in between will just add length, nothing else. Okay, suppose from here I go here, then I come there. This is longer than going straight like this. Okay, so what I can do is I look at all the concave parts, use separating and supporting edges, and remove the other lines. Okay, so in this particular case, which is my supporting line? This is a supporting line. And which is the intersecting line? Intersecting line will be this one and that one. Supporting and separating. So whatever else is coming, I remove it, especially which is here. That is removed. You see, this is removed here. Okay, and this one is removed. That one is not there. So this is a reduced visibility graph. This is a reduced visibility graph. Now, in this reduced visibility graph, now if you want to go from some point to some point, you can simply take this route, this route, this route, that route. You need not go from here to here, go there, go here. These are not required. Okay, so we can have a visibility graph, and then we can have a reduced visibility graph by simply using separating lines and supporting lines. So remove lines that are not on supporting and separating edges to get the reduced visibility graph. Okay, so this is also another example which is showing you a visibility graph. This is showing a reduced visibility graph. Okay, so you can see all unnecessary lines have been removed here. Now, visibility graph method is a very simple method, okay, to find the roadmap and then to take you from one point to another point, as we can very easily find which obstacle to avoid the obstacles. Okay, so this is a very interesting and very easy method. Okay, but if you think a little bit, suppose you are going from one point to another point. Suppose you are starting from this point and you are going from this point, a human being, okay, or maybe even a dog. Okay, well, that's a dog. Okay, a dog is going from the start point to the goal point. Would it follow a path like this? If I were to ask you, would a dog take this path, or would a human being take this path? Which path would you take? Now, we would not take this path. Now, why wouldn't you take this path? Or why is this actually a bad path? Okay, we have found it using visibility graph, using sweep line algorithm and all that. But then why, if you think a little bit, Why is this a bad path? Now this is a bad path because it is going to the edge of the obstacle. Here, here, here. When you go from one point to another point, you don't go and brush against an obstacle, do you? You go far away from the obstacle. Okay? Why? Because it is safer. So this is not safe. Why is it not safe? Because the robot is going, okay, to the vertex, and the vertex is on the obstacle. So if there is any sensor noise or there is any kind of problem in estimation, okay, then the robot is going to go and hit the obstacle. We know that in the real world there are always errors. So the sensors which are there on the robot would have a little bit of error. Let's say ultrasonic sensor or positioning sensor. So if there is small error also, it will go and hit the obstacle. And that is also one reason why human beings, okay, humans, animals, okay, do not do this. We look at the obstacle, maybe make road maps, find a path, and then go. But that path will not be going and touching the obstacle. Okay, that's a bad idea. So the next thing that we do is we look at what is called the Voronoi diagram. Okay, so the generalized Voronoi diagram is a set of points where the distance to the two closest obstacles is the same. So your reduction from 2D to 1D. Okay, now if I go back to this earlier example again, okay, of a human being, which path would you take? So we'll probably take this path. We'll go like this, like this, like this, and go. So what we did is we were equidistant from here, if you see carefully. Okay, we did not go too close to the obstacle. We were equidistant from the obstacles. Okay, that is the safest path. Okay, now if you look at this deformation retract example of cotton candy or sugar candy, you might have seen that if you have the sugar candies which are like this, okay, if they start shrinking from both sides, what will happen is they will go somewhere in the center. Okay, now if I have an obstacle like this, so obstacle 1 and I have another one like this, okay, which is in between both of this. So the path right in between both of this would be here. Okay, so it is like you're going, it is like this is shrinking this side, this is shrinking that side, and then what it is coming is from 2D it has become 1D. Okay, now this is basically how we produce a Voronoi diagram. That is, we try and for different kind of obstacles we have two features. We have edges and we have vertices, right? So any kind of obstacle would be made up of vertices and edges. Okay, and if you want to find a distance relationship which is equidistant, now that's very easy. So basically what we are trying to do is we are trying to get a set of points equidistant. Now suppose this is an obstacle, this is an obstacle, this is another obstacle. Okay, which is the path which is equidistant from here? Okay, so if you have a vertex here, very easy, this point is equidistant. And this line and this line is the same, the angle is the same, right? So it is like, this is the path which is equidistant from both these obstacles. Okay, now if you have a straight line, this is an obstacle, and you have an obstacle like this. Now which is, first of all, start with the vertex, which is the equidistance point, this is the equidistance point. Okay, now this is inclined, this is flat. So what will be the set of equidistance point? This is going to be a curve like this. So these points would be equidistant. Okay, now what about edge like this and edge like this? Now this is very simple. It will be equidistant points will be equidistant from both these edges, which is a straight line again. So in polygonal spaces, obstacles have two features. They can be vertices and they can be edges. Okay, so these obstacles are made, because they're polygonal, they're made up of vertices and edges. And we can have an equidistant relation between them very easily. And now that equidistant relation is going to be the path. Now look at this this Voronoi diagram. These are called Voronoi diagrams. And this is also called a deformation retract. Why is it a deformation retract? Because the example I just gave some time back is that if you're thinking of this shrinking or deforming in that direction, this is deforming in this direction, what you'll be left with is this circle or this curve. Okay, so from 2D it has become 1D actually. Okay, so if you can look at, and that's why it's called a deformation retract. These are called retracts. So we have one side here, another side here. Okay, I start from here. So points which are equidistant to both these points is one line. Similarly, it's one line there, one line here, one line here. These points are all equidistant to two sides. Now there's an obstacle here. So if you can imagine, this obstacle is expanding, okay, and this is also expanding. Where will it come? It will come here. Okay. So this is my network of paths now, which are equidistant from the obstacles and the sides. So path equidistance to obstacles plus edges of workspace. Now this is basically called the Voronoi diagram. Okay. Now in this Voronoi diagram, you are seeing that it is safe, because why? It is going in between the obstacle. It is going in between the edge and the obstacle also. So it's not going very near to the obstacle or the edge. Okay. And this is a deformation retract, because you can think about this as this side is deforming in this direction, the object is deforming in that direction. Where they are meeting in between there. Okay. So this is basically called the deformation retract, or generating the Voronoi diagram, or this is called the generalized Voronoi diagram. Okay, so this is very often called the generalized Voronoi diagram. Okay. Now, once we have got the network of paths, we got the network of paths, which is my roadmap called RM. Then I can go from the start point and join. Okay. Right. So here I can suppose I'm here, initial point, and I want to go here. This is my goal point. All I need to do is to find this node and go and join the node. From here I can find the node and join the node, and then I have different paths. I can go like this, like this, like this, and then that's my path. There can be more than one path. So this is how we can find, either by using visibility graph, we can use Voronoi diagram, we can use deformation retract, which Voronoi diagram or deformation retract are more or less the same. Okay. Okay. To find the network of paths. Once I have the network, then it's a question of just joining the node, the nearest to your start point, and then from the goal, which is the nearest to the goal. And then you can follow the path and go from the start point to the end point. Please note here again that the robot is a point, and we are we are basically dividing this into free space and obstacle space. Okay, that is how we are operating. Now, these are some examples. Another example of finding equidistance point between obstacles is by what is called the Bushfire algorithm for finding retracts. Now, this is very easy, because very easy way of doing it, because in the earlier case you saw that it was something like it was continuous space. Okay, so what you have, this is a geometrical problem, right? So you have the equation of this line, you have the equation of this line. Now you have to take points, one point here, one point here, then find equidistance point. So you have to go point by point. Whereas suppose we can divide the whole space into grids. Okay, then it's much easier for us. The job is simplified. And this is basically called Bushfire algorithm. Why Bushfire? Because if you say, for example, you light a fire. Okay, so we are lighting a fire here. And how the fire will spread is it will start spreading, right? A fire spreads. Okay, like in the forest or in. So you start at one point, then it starts spreading sideways. Okay, in all directions actually. So what we do is we divide it into grids. Okay, and you start putting the obstacle as 1. So obstacle is numbered by, obstacle boundaries are numbered by 1, and increment each adjoining cell by 1. So if this is 1, the next one will be 2, then the other will be 3, like that. And this can be done very easily by the computer. So this is 1, this is 2. So any program can do this very quickly, right? So obstacle was 1, the next one was 2, then 3, then 4, like that. Okay. Now if you see this kind of numbering, then automatically when you have covered the full grid, the highest numbers will correspond to in between points. This is 4, 4, this 5, 5, 5, 5. Okay. Now this is automatic. So between this object and this object, you see this is the deformation retract actually. Now that's automatic, isn't it? Because wherever the number becomes highest, it can't go anymore. And it is going in both directions, from here and here. So the highest number is the one that is in the middle one. So you basically have made your roadmap as shown here. So this is your roadmap, which we have made in this grid format. Now you can start from the start point, join to the node, From the goal point, you can join to the node and then follow the path. Now, here we can also have in 3D. So what I just explained was in 2D. We can exactly do this in 3D also. Okay. So in 3D case, what we do is we deform it in this direction. And this is the wall, the side wall, and this is the obstacle, right? So when we are deforming it, this is my retract now. Now in case of 3D, how will it come? You can see that this is a wall, this side wall is there. This is the floor. So there are 3 lines now, one line here, one line here, and one line here now, the 3 edges. So the deformation retract, what will it look like? So the deformation retract will look something like this. This line is equidistant line, equidistant, and the center line is here. Okay. Now there is of course a top also. Okay, there is a cover is also there of this. So this line is giving you the equidistance line from there. Now if there is an obstacle there, then this is my, for the obstacle it will be like that. Okay. So at the end of the day, what we get is, so it is going to deform like this, and what we get is my deformation retract, which is like this. These are set of points which are equidistant from the side and the obstacle. Okay. So we'll stop here today, and in the next class, today we looked at manifold, then we looked at the rotation matrix, and from the rotation matrix, we then moved on and looked at the roadmap method. And in the roadmap method, we basically saw that once you have a roadmap, then in the roadmap from the start point, you can connect to the roadmap, and from the roadmap and from the goal also, you can connect to the roadmap, and then find different paths that will take you from the initial point to the final point. And we looked at a few methods of finding the roadmap, for example, using visibility graph, then by using deformation retracts. Okay. So we'll stop here today and we'll continue in the next class. Thank you.